It all works together in that way. So let's see if we can think of, before I give you a problem, which is coming up, let's talk about resistance just a little more, and that is what would cause a lot of resistance and what would cause a little resistance. So if we have a material that is wide conductor, and if we have a conductor that is narrow, that will affect our resistance. So which is which, do you suppose? MK, do you think the wide would give more resistance or the narrow? Actually, because there are a bunch more electrons or a bunch more atoms in the wide, that actually gives you more. So if you would indicate that, the wide, no, I'm sorry, she's right. Nope, I'm right. All right, so let me check just to make sure. The wider it is, you're right, she's right. The wide conductor is low resistance. Here's what I was thinking of. I was mixing it up with the next one. Lower, and so MK, explain your thinking again. It was correct. Lower, and this is higher.
Because there's less space and they're bumping into each other more when they go through.
All right, so if it's wide, they have more paths to get around those atoms. When it's narrow, there's a lot more bumping. Okay, so the resistance is higher when the material is narrow. Higher resistance, narrow. Lower resistance, wide. Here's what I was getting it mixed up with. What about a longer conductor and a shorter conductor? Try that one, MD.
Oh.
It's okay, you can be wrong. I was just wrong, so.
I would think that the longer conductor had a higher resistance.
It's right.
Because it got more space.
All right, so higher resistance for the longer, and why?
Because there's more space for it to go through, so it takes like longer and it's
Get
gonna
more
bump
atoms
more.
to bump into, right? Shorter conductor is lower. All right. All right, so you've got the idea of that. All right, using V equals IR, we actually call that Ohm's Law because the guy who found it or discovered or noticed it, Ohm's Law, his name was George Simon Ohm, and he is remembered by calling it Ohm's Law. Let's use Ohm's Law, shall we not? All right, in order to use Ohm's Law, we're going to put it together with drawing electric circuits. So we've kind of drawn our first one, but I'm going to show you the formal way that an electrician would understand. So you can leave here and go apply for your electricity license.
Yeah.
Got to know what you're doing when you're in that field.
Yeah.
No mistakes allowed. So, all right. So let's say we are drawing a circuit, and the official way is to draw a long line for the positive side and a short line for the negative. So for a while I'll put a plus sign by the long line and a negative sign by the short line. And to remind you, but in a real drawing, it's understood that the long line is the positive and the short line is the negative. So then they go like this, and you draw the official circuit. It's always square, even if you're wiring a round room. This is the way you communicate to your other electricians what the path looks like. It starts from the positive and goes to the negative with a long line and a short line. Now, when we do that, we have a positive. It's kind of funny how we do this. I don't even know how to explain it except to say it. It's kind of lame, but out with it. I can do this. Turned out Ben Franklin, he figured this kind of stuff out a long time ago. And he said, he envisioned that the plus side was where there was a surplus of, he didn't know about positive and negative charges, but he knew something was running through something. So he said there's a surplus of these mystery particles, we'll call them, because that's all it was to him. And over here, there was a lack of mystery particles. So the surplus of mystery particles would run, and when you draw a circuit, you draw dotted lines along the interior, parallel to the edges, and then you indicate at the end which way they're moving. So Ben Franklin drew his electric circuits where he was going from positive, which was in his mind, a surplus of mystery particles, to the negative, where it was where there was fewer electrical particles. And we can write the letter I, because this is amperage, this is the actual flow, current. This is current, and I introduced the word current with the letter I for those physicists, sorry that can't spell. So I is for current, so dot it in and go from positive to negative. Now that we understand it better, we still don't have a great grasp on electricity, but understanding more of it, is this the correct flow? Like when we had our battery here, to us, what did positive mean? Positive, and what did negative mean? Did you catch that?
The opposite, yeah.
Yeah, so would you explain that, MM? So negative meant there was an excess, right, of negative electrons.
Yeah.
Yeah, and this is the material that wants to lose electrons. So it has excess electrons, so its charge would be negative. Would that not flow to the positive side?
Yeah.
So now we know, and there were years, decades, where electricians followed Ben Franklin's way and drew it like this. Now we know it goes like this. So this is called conventional flow. It is wrong. But guess what? We all decided to stick with it. So
Wait, what?
we still do it that way. So we still use the conventional flow in our diagrams. So when I taught you battery, I taught you the negative flows to the positive, and on our electrical circuit drawings, we're going to draw it incorrectly. But it's okay, because all of our lights and all of our appliances work the same whether we draw this way or that way. All the formulas come out the same. The direction doesn't matter. Really, when we plug in, did you know, I'm sure you do, when you plug into a circuit, it's alternating. The flow goes one way and then the other like a million times a second. So the actual direction doesn't really affect any of our real life results. So instead of taking all the books before 1900 and changing them after 1900, we decided to keep the conventional flow because it didn't affect anything anyway. So, one year, what did I do? One year I taught this way, not saying all this the first day. I taught it this way. I just said electricity flows from positive to negative, and we did all of our problems, took the test, and then I stood there and told them it was wrong. It did not go well. So I'll tell you that it's wrong from the beginning and see if you can handle it better. All right, it's wrong, but all of our formulas will work the same and all of our electrical appliances will work the same. So we just draw them this way from positive to negative, and it's almost just nomenclature. It doesn't affect anything.
So the real one goes from negative to positive. Why?
Because then where there's, like in the battery I just showed, where there's a chemical or a situation where there's an excess of negative particles, they want to give away their electrons. And this is the part that wants to gain electrons. So the giver goes to the needer. All right, so the giver goes to the need. So it is opposite of what Ben Frank, he only had so much to go with, and he still, everything he said came true. I mean, we use it and it works. So we'll honor him by drawing our diagrams the wrong way. We still draw circuits this way. All right, let's go ahead then and see what happens when we put some resistance into our circuits. So I've talked about amperage right here, and the voltage will be listed here in our circuits, and the resistance will show up as a wavy line. So let me give you all of that together in one drawing, and it will look like this. Let's do a plus and a minus. See, I'm not drawing in the plus or minus. You know the longer side represents plus. And you're going to go around, and right here you're going to do a wavy line like this. If you've ever seen electrical drawings, you've seen these before. That is where the resistance is. So this is a resistor. Such as a toaster. Did you know a toaster is a resistor? So what happens with our toasters, we send an electric flow through the toaster, and when it gets to the resistor, that is a material where electrons will start bumping more. So here it has an easy flow. When it gets to the resistor, it has impediment. It's going to be impeded in some way by a new material or a different shape, and the flow of electrons is going to be resisted through here. That resistance causes more bumping. What does the more bumping cause? Heat. And so we have our toast. So you can call your toaster a resistor and be completely accurate. So.
Should we start it again?
Oh yeah.
Pretty sure I went over.
Probably went over it. Okay. I can cut it in half. I know how to do that. Thank you.